Alright, in this recording we want to delve into some of the details of controlling prokaryotic gene expression. Now, we've already talked about this idea that bacteria are going to respond to their environment, and in general only bring in machinery that they need when the raw materials are available for that. And we use the tryptophan synthesis pathway as an example of that. This also correlates then to the trip operon, this cluster of genes under one promoter region that says when we need these enzymes to make tryptophan, we turn them all on and they go to town, or when we don't, we shut them down. Excuse me. So again, to review, we have this idea of putting a cluster of functionally related genes under the control of one switch, and that is by definition the operon. So remember that switch is called the operator. So it's a sequence of DNA that's going to bind something, a protein in this case, that allows you to turn transcription of this group of genes on or off. So again, here we go. Here's our promoter region, then we have our operator, then our specific genes for the biosynthetic pathway. Pardon me. Now, the operon, any operon, can be defined a couple different ways. So operon control can be repressible, meaning that by default, expression of these genes is on, and then something has to happen to turn them off. It can be inducible, meaning the default is off, and that something has to happen to turn them on. Now, beyond that, you can also talk about negative control, meaning you have an active repressor protein that's preventing transcription, so you're doing something to shut it down. Or you can have positive control, where transcription is stimulated by an activator protein. So now you're doing something to crank up gene expression. And as we're going to go through the examples of the TRIP and the lac operon, we're going to see each of these and their role. So repressors. Let's focus on this idea of a repressor. So if the default for an operon is on, a repressor can turn it off. And what it's going to do is it's going to prevent gene transcription by physically blocking RNA polymerase. Now, so this is the point that I want you to get in your head. This is machines. These are like tiny little machines. There's nothing magical about them. And when you put like a barricade in front of a car, the car can't move through it. It just doesn't go because there's something in the way. And that's going to be how this works. If I put a protein on the DNA that binds and doesn't move, the RNA polymerase can ram into it, but it can't move forward. It's going to be blocked. Right? So it's very physical. This is a very physical process. So the repressor is literally, it's a protein. It's the product of a different gene. So that whole control of gene expression of that other gene is going to affect expression of the operator. But we're not going to even worry about that now. We're just going to worry about the fact that there's a gene somewhere else in the genome that encodes for this protein that is the regulatory gene for this particular operator, whatever operator that may be. Now, that protein could be either in an active form or an inactive form. And this is when we talk more and more about proteins and enzymes, we'll see that there are lots of ways to turn proteins on and off. And in this case, there's going to be a co-repressor molecule that's going to bind to the repressor protein and turn it off. Now, the best thing to do is to get into this is start to look at pictures. But what we want to remember is that the trip operon, as we get specific, is by default on. Right? When tryptophan is present, it's going to turn things off because tryptophan is in fact the co-repressor of the repressor protein. It's going to bind to it, activate it, and allow it to bind to the DNA to say shut this thing down. Right? So if we look here, we see on the left side of the screen there's a promoter and a TRPR gene. That's the trip regulator gene. So that's going to let's just assume that's going on its own way. It's making RNA, it's making the protein. We've got this protein that is the repressor. And you can see by its shape, it has this funny shape of these two little knobs on top that kind of look like they could fit into the operator. If we look on the right side of the screen now, you see the trip operon, and there's RNA polymerase. And it's going to ride right over the operator and start to transcribe these genes that will be made into enzymes that can help us make tryptophan. Now, what we're going to see is that tryptophan itself can bind to the repressor and activate it. So you're going to activate the repressor to shut down the operon. So you turn one thing on to turn another thing off. How does it turn on? It binds to the product of the biosynthetic pathway. Now this has changed shape, again form and function. That shape now fits and binds into the operator, and as it binds, it then prevents RNA polymerase from moving forward. We've effectively shut off this operon. Why have we done that? Because we have plenty of tryptophan. Tryptophan binds, activates the repressor, repressor shuts it down. More efficient. All right, so let's explore kind of a different approach where we still have a repressor, but in this case the default is off. So we have to induce expression of the lac operon. So the lac operon is going to encode for those enzymes that are responsible for bringing lactose, a sugar, into the cell and breaking it down so that it can be used for energy. So by default, this operon is going to be off, and we only want to turn it on when lactose is present. So what we're going to see here is now somewhere else in the genome, this protein that is the repressor for the lac operon is produced, and in this case, the default for this protein is always to be on and active. So it's preventing RNA polymerase from ever making any of the lac operon genes. All right? Now, along comes allolactose, which is, we're just going to shorten that to lactose for now. So here comes this sugar, and when the sugar is present, it's going to bind to the protein and change its shape so that now it cannot bind to the promoter. It can't bind to the operator. So RNA polymerase now has a free rein to go ahead and make the genes that are necessary to bring lactose into the cell more abundantly and to break it down so that it can be used for energy. Okay. So inducible enzymes usually then function in what we call catabolic pathways. So this is the point I want to make. So catabolic versus anabolic. Repressible enzymes usually function in anabolic pathways. So you want to think catabolic is enzymatic pathways that break things down. All right? Anabolic pathways are pathways that build things up. So with the case of tryptophan, it's an anabolic pathway. This is something I must have. And so the default is going to be on. And when I don't need any more, I'll turn it off. When I fall below the threshold of what I need, I automatically turn on again. You want that, because if you don't have tryptophan, you'll die. Catabolic says, I'm going to break things down for energy. Well, I don't want to have all this machinery around if there's nothing to break down. So in this case, I'm usually going to make it inducible. I'm going to say, hey, when this thing that I can break down shows up, induce the expression of the machinery needed to break it down. Now, what we've seen here is negative control in both these cases. What we want to consider next is kind of pushing the lac operon in the other direction to positive control and looking at upregulation by another protein called the catabolic activator protein, or CAP. So it's going to be an activator of transcription. It's actually going to help load RNA polymerase on at a higher level and keep transcription up and running at a greater intensity. So now what we're going to explore, and people tend to need to hear this more than once, so you may have to go over this part of this recording a couple times to kind of really get it in your head, but I do want you to understand this. This is how you can make decisions on a cellular level with just switches, with just molecular machines. All right? So what I'm going to do is show you how a cell can have a preference for one carbon source, one energy source over another. So if we use E. coli as our example, glucose is preferred. It's preferred over lactose. All right? And glucose is easier to use because you can feed it into these fundamental biochemical pathways much easier than lactose, but there's a preference there. So how do you set up a system that prefers one carbon source over another? We're going to use this upregulation and downregulation. Now, what we're going to see is that when there isn't glucose around, we're going to see the increase in cellular concentration of what's called cyclic AMP. And you can see that as that little orange diamond here. Now, so as glucose goes down, cyclic AMP goes up. cyclic AMP then binds to the cap protein, activating it, and that then binds to the promoter of the lac operon and says, go, 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 RNA polymerase. Like, I'm going to load you up even faster than you would normally go. I'm going to upregulate this gene. Now, if lactose is present, it will have bound to the repressor protein, inactivating it, allowing that higher level of RNA polymerase to be loaded and make many, many, many transcriptions of the lac operon. So we have plenty of machinery breaking down lactose to make energy because glucose isn't present. All right? Now, if glucose is present, what we're going to see is no cyclic AMP around, and CAP is never activated. If CAP is never activated, we will get what's called a basal transcription level, and RNA polymerase can bind to the lac operon. And if lactose is present, the repressor won't be present, but you'll get a much, much lower level of transcription. So what we want to think about is when glucose levels increase, CAP will become inactive, and we don't get this upregulation. We've taken the bonus out of it. All right? So this is really the slide that I like to kind of break down this control mechanism with. And so what we can see here across the top is a diagram of the lac operon. And then we have all four possibilities: low glucose with lactose, high glucose with no lactose, no glucose, no lactose, and then finally high glucose and lactose. And so what you want to do is be able to walk through each of these and understand what's upregulating, what's downregulating, what's negative control, what's positive control. So if we have low glucose and lactose is available, we have positive control. We're going to crank up on the transcription of this operon. So cyclic AMP has been activated because glucose is low and cyclic AMP is high. It's going to actively load RNA polymerase onto the DNA. Because lactose is available, the repressor has been inactivated, and RNA polymerase can go ahead and transcribe. So we call this constitutive levels of expression, high levels of expression. Now, if we look at a different situation now where we have glucose, but lactose is unavailable, the cell prefers that. That's a better situation. So there's not going to be much cyclic AMP. CAP is not active. There's no lactose available, so this whole operon is actually shut down by the repressor as well. Tuck it away. I don't want that. I don't need it because I have plenty of glucose. Now, our third situation is we don't have glucose, but we don't have lactose either. So the cell's going to be trying to find more energy. So cyclic AMP is going to be high, activating CAP protein. CAP's going to be trying to load RNA polymerase onto the lac operon as an alternative energy source, but because there's no lactose present, the repressor protein is active, is bound, and says, don't waste your time. Don't waste the precious energy that we have making machinery for something that isn't even here. So finally, then, you can have high glucose and lactose available. So this is now the cell showing its preference again for glucose. Because glucose is present, there's no or low levels of cyclic AMP. CAP is not active. But if lactose is present, the repressor protein will be inactivated. So RNA polymerase can load, but it's not going to be upregulated, right? So we get what's now called basal levels of expression, which will be low levels of expression. And that's fine because you're not putting most of your eggs into this basket. You're putting most of your eggs into your preferred basket of glucose metabolism, right?